Welcome. In this video, we will dive into the fascinating world of electrical charges. These charges form the very fundamental of electrostatics. And every other topic in this unit builds upon this core concept. Once you grasp the idea of charges, the rest of electrostatics will become much clearer and easier to master. So stay with me until the end and let's uncover the secret together. Presenting Book on Electrostatics, a complete guide designed to cover the entire syllabus of class 12th and competitive entrance examination. Written in a very simple language, this book ensures that anyone can easily understand even the toughest concept. Packed with detailed diagrams, figures, plenty of solved and unsolved numericals, it makes learning more interactive and concepts crystal clear. Dive in and master electrostatics with ease. And let's start with the fundamental question. Where do these charges come from? The answer lies in atoms. In the basic atomic model, we have seen how negatively charged electrons revolve around a positively charged nucleus, much like planets orbiting the sun. To truly understand electrostatics, we need to grasp the key features of an atom. An atom consists of three fundamental particles: negatively charged electrons, positively charged protons, and neutral neutrons. The charges on an electron and a proton are equal in magnitude at 1.6 into 10 to the power of minus 19 coulombs. In every atom, the number of electrons equals to the number of protons. Because these positive and negative charges balance each other perfectly, the net charge on an isolated atom is always zero. When we think about charge on a substance, it all starts at the atomic level. Each substance is made up of atoms, and their charges arise from the negatively charged electrons and positively charged protons. Here in this figure, an atom can be represented by a circle with a positive charge and a negative charge, and a substance which is made up of millions and millions of atoms can be represented by this diagram. The overall charge on the substance is a result of the negative charge on all its electrons and the positive charge on all its protons. It is hard to believe how the smallest building block of matter holds the key to understand the charges in the world around us. A fascinating fact about substance is that when the negative charge on all the electrons equals to the positive charge on all the protons, the net charge becomes zero. We call such a substance as neutral or uncharged substance. But here, there is something more interesting. If someone asks you whether an uncharged substance contains charges, the answer is resounding yes. It holds equal amount of positive and negative charges, perfectly balanced, the resulting in the net charge equal to zero. Now, a question arises: how do we define a charge? Charge on a substance can be explained in terms of number of electrons present in that substance. Especially, charge on a body depends on the balance between the number of electrons and protons it contains. If the number of electrons exceed the number of protons, the body has excess of electrons and it is said to be negatively charged. Conversely, if the number of electrons present in that body is less than the number of protons, there is a deficiency of electrons, then the body is considered to be positively charged. Thus, charge can be defined as a result of an excess or deficiency of electrons in a body. A body becomes positively charged when it has fewer number of electrons than protons, which creates an electron deficiency. But how this deficiency can be created? The answer is simple: by removing electrons from that body. By taking out electrons from that body, we can convert a neutral body to a positively charged one. A body is said to be negatively charged if the number of electrons in it exceeds the number of protons, meaning there is an excess of electrons in that body. Now the question arises, how can this excess of electrons be created in an? The answer is straightforward: by adding electrons to that body. By introducing additional electrons to a neutral body, we can transform it into a negatively charged one. You can see this in this diagram, that we had added electrons to this neutral body to make this body negatively charged one. Charge is always associated with matter. A neutral body can be transformed into a positively charged or negatively charged one by either removing or adding electrons to it. Electrons, being particles of matter, have mass. Specifically, the mass of an electron is approximately 9.1 into 10 to the power of minus 31 kilograms. This means that when you add or remove electrons from a body to impart charge to it, we are also altering its mass. For instance, a neutral body can become positively charged one when electrons are removed from it. Consequently, the mass of the body decreases by an amount equal to the mass of the electrons that has been removed. In this figure, we have got a positively charged body which has been converted from a neutral body by removing electrons from it. If earlier the mass of the body was m, now the mass will become m minus delta m. Delta m corresponds to the mass of the electrons which has been removed from that body. A neutral body can be transformed into a negatively charged one by adding electrons to it. Since electrons have mass approximately 9.1 into 10 to the power of minus 31 kgs, adding electrons to a body results in increase in its mass. Therefore, when a body is given negative charge, its mass increases by an amount equal to the total number of electrons which has been added to it. Here, this body is negatively charged, which has been created by adding electrons to that body. If earlier the mass of this body was m, now this mass of this negatively charged body will become m plus delta m. Delta m corresponds to the mass of the electrons which has been added to that body. It means mass of the negatively charged body will be more than the mass of the neutral body from which this body has been created. There are few important points to remember here. Firstly, charge cannot exist in vacuum. Since charge is associated with matter, there is no matter in a vacuum. Charge cannot exist in such an environment. Secondly, the mass of an electron is extremely small, approximately 9.1 into 10 to the power of minus 31 kilograms. When a neutral body is charged, its mass changes by a very small, practically negligible amount due to addition and removal of electrons. As a result, in a day-to-day life, this change in mass is not considered, it is not taken into account. Lastly, according to Einstein's special theory of relativity, the mass of a body increases as its velocity increases. However, this increase in mass does not affect the charge present on that body. In other words, the charge on a body remains constant and is independent of velocity. Now, there is one more property of charges, that like charges will repel each other and unlike charges will attract each other. a positive and a negative charge. These are unlike charges, they will always attract each other. And like charges, two negative charges and two positive charges will always repel each other. This is one of the basic property of electrical charges. One of the important properties of charges is the conservation of charge, which states that the total amount of charge in an isolated system always remains constant. Although equal quantities of positive and negative charges can appear or disappear simultaneously, their net charge remains unchanged. When equal quantities of positive and negative charges appear simultaneously, the process is called pair production. For example, when gamma rays, which are neutral, are passed through a strong electric or magnetic field, they can split up into negatively charged electron and positively charged positron. In this process, the pair of opposite charges appears simultaneously, forming what is known as pair production. You can see gamma rays are made to pass through a very strong electric or magnetic field. Then this gamma ray will get split up into two charged particles, positron and an electron. A positron, it should be noted that it is an antiparticle of an electron. Conversely, when a negatively charged electron and a positively charged positron combine under special conditions, they get converted to neutral gamma rays. This process, in which positive and negative charges disappear simultaneously, is known as annihilation of charge. Another fundamental property of charge is quantization of charge. This means the charge exists in discrete packets. The smallest packet or the smallest unit of charge is a charge on a single electron or a charge on a single proton, which is approximately 1.6 × 10⁻⁻19 coulombs. Hence, the charge on a body is always an integral multiple of charge on an electron. If Q is a charge on a given body, then Q is always equal to plus or minus n into E, where E is the electronic charge, which is 1.6 × 10⁻⁻19 coulombs, and n is a positive or a negative integer. The explanation of quantization of charge is very clear and very easy. That is, when you give charge to a body, we add or remove electrons from that body. The more the number of electrons added or removed will determine the amount of charge acquired by that body. If we remove 2 electrons from a neutral body, the body will acquire a charge equivalent to plus 2e, a positive charge of 2 times the electronic charge. On the other hand, if you add 4 electrons to a neutral body, the charge acquired by that body will be negative 4 times the electronic charge, that is minus 4e. You can see in these animated diagrams that this body will acquire a positive charge of plus 3e when 3 electrons are removed from this body. This body will acquire a charge of minus 3e when 3 electrons are added to this body. One of the important things to remember is that the magnitude of positive charge on a proton is equal to the magnitude of negative charge on an electron. And there is one basic question which is asked many times in your exam, that how many electrons are to be removed from a given neutral body to give that body a positive charge of 1 coulomb. This question can be solved by using the concept of quantization of charge. According to quantization of charge, Q is equal to N into E. Q is equal to 1 coulomb, which is the charge given to us. E is the electronic charge, 1.6 × 10⁻⁻19 coulombs. and n is the number of electrons which are to be removed. By cross multiplication, n will become Q upon E. Q is 1 and E is 1.6 into 10 to the power of minus 19 coulombs. If you solve it, it will become n is 6.25 into 10 to the power of 18. That means 6.25 into 10 to the power of 18 are the number of electrons which are to be removed from a given body to give that given body a positive charge of 1 coulomb. Charge is not a fundamental physical quantity. We have done earlier in class 11th that there are 7 fundamental physical quantities. They are mass, length, time, temperature, amount of substance, that is mole, current, and luminous intensity. We do not have charge included in the fundamental physical quantities. Then what is charge? Charge is a derived physical quantity. Charge can be derived by using the concept of electric current and time. Electric current, as we have done in our lower classes, is defined as the rate of flow of charge. If I is the representation of electric current and dq is a small amount of charge which is flown in time dt, so I will become dq upon dt. By cross multiplication, dq will become I into dt. That means charge is equal to product of current and time. Charge is equal to I into T. The dimensions of I, current, is ampere and dimensions of T is T. So A1 T1 will be the dimensional formula for charge. Since charge is again a physical quantity, it should have some dimensions and it should also have units. What are the units of of charge? The SI unit of charge, standard international, are coulombs. How do we define 1 coulomb? 1 coulomb is that much amount of charge which can be flown through a conductor which is carrying a current of 1 ampere in 1 second. And 1 coulomb is a big unit of charge. We do have smaller units. We have got millicoulomb. 1 millicoulomb is 10 to the power of minus 3 coulombs. 1 microcoulomb is 10 to the power of minus 6 coulombs. 1 nanocoulomb is 10 to the power of minus 9 coulombs. 1 picocoulomb is 10 to the power of minus 12 coulombs. These are the small units which we take of charge. Otherwise, 1 coulomb, which is the SI or MKS unit, is a very big unit. When you give positive or negative charge to a soap bubble, either by removing electrons from that bubble or by adding electrons to that bubble, the positive or negative charge will always be residing on its surface. Since like charges repel each other, that means all the charges which are present on the surface will be repelling each other, will be pushing all the charges away from the center. And as a result, the bubble expands. Whether it is negative or it is positive charge, when it is given to a soap bubble, it always expands. When positive or negative charge is given to a solid or hollow conductor, then this charge resides on its surface. Since like charges repel each other, hence all these charges will try to go away from each other and hence they will be residing at the surface of the conductor. Even if you will keep the charges at the center of the conductor, even then they will repel away and they will be going to the surface. In any case, whatever be the shape of the conductor, if it is charged, will have charges on its surface. When we talk about uniform distribution of charge on a body, then there are 3 kinds of distribution of charges. The charges can be distributed uniformly in both conductors and insulators. First, uniform linear distribution of charges. Second, uniform superficial distribution of charges. And third, uniform volume distribution of charges. We'll take up each distribution one by one. Now, linear charge distribution. Charge is distributed uniformly on a given line. If delta Q is a small amount of charge which is distributed on a length delta L, then the lambda, the linear charge density, is given by delta Q upon delta L, that is charge per unit length, or dq upon dl. If you want to find out the total charge or the total length, then it can be done by integrating dq from 0 to q, or dq is lambda into dl by cross multiplication. It is from L1 to L2. Since lambda is a physical quantity, what will be the units of lambda? SI or MKS units. It's coulomb per meter. It is charge per unit length. And what will be the dimensions of lambda? Again, it is dimensions of charge per unit length. Charge has got dimensions A1, T1, and length is L1. It will be A1, T1, L minus 1. This will be the dimensional formula for lambda, that is linear charge density. Surface charge distribution. Charge is distributed on a given area. If delta Q is a small amount of charge present on a small area delta A, then sigma, the surface charge density, that is charge per unit area, can be calculated by calculating delta Q upon delta A, or dq upon dA. The total charge on the whole area can be calculated by integrating dq from 0 to q, and dq by cross multiplication is sigma into dA, and it can be integrated from A1 to A2 to calculate the total charge. Since sigma is again a physical quantity, so what will be its units? The units of sigma are coulomb per meter square. And what will be the dimensions of sigma? Charge per unit area. Charge has got dimensions A1, T1, and area has got dimensions L square. So dimensions of sigma will be A1, T1, L minus 2. So this will be the dimensional formula for surface charge density, that is sigma. Volume charge distribution. Here charge is distributed in a given volume. If delta Q is a small amount of charge which is distributed in a small volume delta V, then volume charge density, that is charge per unit volume, rho, is given by delta Q upon delta V, or dq upon dV. The total charge in the whole volume can be calculated by integrating dq from 0 to q, and dq is rho into dV. It can be integrated from V1 to V2. Again, rho is a physical quantity. What will be the units of rho? Rho will be coulomb per meter cube, because volume has got units meter cube. And what will be its dimensions of rho? Will be charge per unit volume. Charge has got dimensions A1, T1, and volume is L cube. The dimensional formula for rho will be A1, T1, L minus 3. This will be the dimensional formula for rho, that is volume charge density. Now let's explore the different methods of charging a body. There are numerous ways of charging a body. Three fundamental methods stand out. The first method is charging by friction. This involves rubbing of one body against another, causing a transfer of charge between them. The second method is charging by conduction. Here, a charged body is brought in contact with another uncharged body, resulting in the transfer of charge. And the third method is charging by induction. In this process, a body is charged without any physical contact. Instead, it occurs from a distance, relying on the influence of a nearby charged body on the another. We will dive into each method one by one in detail. Charging by friction. We should remember one thing, that every element or substance is unique and have their own properties. Some elements or substances can lose electrons easily, while others can gain electrons easily when they are rubbed against each other. Let there be two substances, A and B. Substance A has a tendency to gain electrons, while substance B has a tendency to lose electrons. Now, when these two substances A and B are rubbed against each other, then the electrons will be getting transferred from B to A, because A has a tendency to gain electrons and B has a tendency to lose electrons. Hence, the substance A will acquire negative charge and the substance B will acquire equal amount of positive charge. Now, up to this topic it is clear. But now the question arises, how we will come to know that which substance will become positive, which substance will become negatively charged when they are rubbed against each other, and electrons will be getting transferred from which substance to which substance. Scientists have conducted a number of experiments and studied the properties of different elements. They had formed a series of elements to determine how the transfer of electrons will take place. From that series are rubbed against each other. Which element will become positively charged and which element will become negatively charged. This series is known as triboelectric series. Now you can see that this is a very small portion of that triboelectric series. Actually, this triboelectric series is very long and you can see the entire triboelectric series on the internet. To read this triboelectric series, we have to remember one thing. We can choose any two elements from that series, and the element which will be nearer to the top will acquire positive charge, and the element which will be nearer to the bottom will acquire negative charge. We'll take up an example. Suppose nylon is rubbed with wood. Nylon is at the top of the series and wood is at the bottom of the series. Therefore, nylon will acquire positive charge and wood will acquire negative charge. The electrons will be getting transferred from nylon to wood. So this is how you can read, this is how you can come to know that when different elements are rubbed against each other, how the transfer of charge will take place, how the bodies will get charged. Charging by conduction. Charging by conduction takes place when the two bodies they are brought in contact. Let there be two spherical bodies, body 1 and body 2, having radius r1 and r2 and charges q1 and q2 respectively. When these two bodies are brought in contact, the total charge on them will be q1 plus q2 and the two bodies will acquire common potential and the charges will be redistributed. There will be a transfer of charge between the two bodies when the two bodies are brought in contact. And this transfer of charge, we call it as conduction. And again, when the two bodies are separated from each other, the final charge on each body will be depending upon its radius. the charges will be redistributed according to the radius. The one which is bigger in radius will have more charge. The one which is smaller in radius will have less charge. Now this is how the charges will get redistributed. Now we can take up the same process in this way. Let there be two spherical bodies, body 1 and body 2. Body 1 has got a charge q1 and it has got a radius r1, and the body 2 has got a charge q2 and radius r2. Both the charges may be different, maybe q1 is bigger or q2 may be bigger, whatever be the case. When the two bodies they are brought in contact, the total charge on them will be q1 plus q2 and they will be acquiring common potential. Now in this situation, when the two bodies they are in contact, there will be a transfer of charge between them. This transfer of charge we call it as conduction. The charges may go from body 1 to body 2, or it can even go from body 1 to body 2 or from 2 to 1. Now when again the two bodies are separated from each other, the charges will be redistributed according to the radius. The one which is bigger in radius will have more charge, the one which is smaller in radius will have less charge, irrespective of what they had earlier. The body 1 was earlier having a charge of q1, now the charge will be q1 dash, which will be r1 upon r1 plus r2 into q, where q is the total charge present on the two bodies. The final charge present on body 2 will be q2 dash, which is r2 upon r1 plus r2 into q. Now this is how the charges are getting redistributed due to conduction. The whole process can also be represented by this way. We had two bodies, body 1 and body 2, having different radius, different charges. When they were brought in contact, the total charge on them will be q1 plus q2 and they will acquire common potential. At this stage, there will be a conduction of charge between the two bodies. The charge may go from body 1 to body 2 or from 2 to 1, but the charges will be getting redistributed. When again the two bodies are separated from each other, the charge acquired by body 1 will be depending upon its radius, and the charge acquired by body 2 will be also depending upon its radius. More the radius, more will be the charge acquired by them, and the final charge will may become different from the initial charges on the two bodies. We can even have a situation in which the body 1 is charged and the body 2 is uncharged. Now if the body 2 is uncharged, in that case q2 will become 0, and we have the same process in this way only, but in the whole process we will put q2 equal to 0, and finally the body which is uncharged will also have charged. The body which is charged, the charge will decrease from body 1 and the charge may go to body 2, but the total amount of charge in this case will always remain constant. Charging by induction. Charging by induction is a process of charging a body from a distance without making a physical contact of a charged body with the uncharged body. Again, we can take up an example. Let there be two bodies B and body C. Both the bodies are uncharged, and both the bodies B and C, they are placed in contact with each other. Then when you bring a body A which is charged, and we are keeping the body A at some distance from body B and body C, then what will happen? Then the negative charges will be getting negative charges in body B and C will be getting attracted towards the body A, and they will get collected in body C. The positive charges in body B and C will be getting repelled from body A, and they will be getting collected in body B. Now as a result, the negative charge will be collected in body C and positive charge will be getting collected in body B. Now in the next step, what we did, we had separated the two bodies. Now the charges will not be conducted further. the body C will acquire negative charge and the body B will acquire positive charge. Now in the next step, we had removed the body A. Now the two bodies has been charged. We have charged body B and body C. Earlier they were neutral. Now the body B will be positively charged and the body C is negatively charged. We had charged the bodies B and C with the help of body A, but without bringing the body A, which is charged body, in contact with the uncharged bodies. This is how we can say that charging can be done by induction. Electroscope. Electroscope is an early scientific instrument that is used to detect the presence of charge on a body. It is made up of conducting sphere which is attached to a metallic brass rod, and at the rear end of the metallic brass rod there are gold leaves. The gold leaves along with the brass rod, it is enclosed in a glass container, or we can call it as glass bottle, so that the air will not disturb these leaves. What are the main parts of the electroscope? First is conducting sphere. It is a metallic conducting sphere which is usually made up of brass, and it is used to acquire the same charge as that on a body. The second part is conducting rod. The metallic sphere is attached to the conducting rod. This conducting rod is also made up of brass. Then why do we choose brass? We choose brass because brass is a very good conductor of electricity. And this brass rod, it is attached to two gold leaves. Now these gold leaves, they are attached to the rear end of the brass rod. These two leaves, they are very flexible, they are very light, and they are made up of gold. Why do we choose gold? Because gold is highly malleable. It can be beaten in the form of very thin sheets. Then the last part is glass chamber. So we are protecting the gold leaves from the drafts of air so that the air should not disturb these leaves. Now how it works, the working of electroscope. So if the metallic sphere is neutral, the not gets separated from each other because there is no charge here. Now but when you connect positively charged body to the metallic sphere, the positive charge will be conducted through the brass rod to the two gold leaves. The gold leaves will acquire similar charge and they will get separated from each other. Now the separation of the two leaves show that this body has got some charge. We can even connect a negatively charged body to the metallic sphere. The negative charge will be conducted through the metallic rod to the two gold leaves. The two gold leaves again, they will get separated. From the separation of the two gold leaves, we can conclude that this body is again charged. Now if you see that whenever the leaves will get separated, it means that some charged body is connected to the metallic sphere. Whether the body is having positive charge or the body is having negative charge, in both the cases the leaves will get separated. And if the leaves are not getting separated, it means that the bodies are uncharged.